Our next speaker is Bingjie Wang from Oscar Health.
Hello. Thank you. Hi. Hello. Is this working? All right, cool. So, I'm from Oscar Health. I'm a software engineer here, and here today we're here to talk about, coming up with provider recommendations and how to rank them. So, a little bit about Oscar. We're a tech-first insurance startup. We started about 7 years ago, and one of our missions is to basically drive engagement with our members and use that to make healthier life accessible and affordable for all. So how we do that is with a lot of tech-driven tools. So for example, each member is assigned with a concierge team, and their concierge team's internal tools are powered by tools built by Oscar. Another one is sort of routing our members to doctors, facilities, and drugs, as well as integration with health tech. So today we'll be focusing mostly on how we route cares to providers. So this is a demo of our tool. So for example, you look for a throat doctor. There's a free text search where you can, it tries to actually understand throat doctor and map that into ENT. And it gives you then a display of, here are all the providers all the ENTs in New York, and it gives a recommended list. All right, and then you can click into a particular provider, and it'll display, the various information about that provider. So sort of at the core of our product is, the ability to actually recommend high quality and low cost providers. So, it gives us, our members, access to low cost and affordable care. Cool. So what really powers our recommendation engine is the fact that as a sort of tech first payer, we're at the convergence of all this data. So if we get incoming claims, that tells us about, how expensive they are, whether or not there was an escalation, and the clinical outcomes. We also get a lot of member interactions because we have an app, and the concierge team that we mentioned before. If you have a problem, you tell them, and that gives us feedback. Also, we get provider roster data as part of as our insurance, as an insurance ops, and we contract. And finally, we have provider integrations. You tell us what you want, and we'll try to use that during our rankings. So, we're here at a machine learning conference, and we have to I'm here to make the case for how machine learning helps us. We used to use a rules-based approach, and it works great. It works great, but since we have so much data about all of our providers, the problem ultimately comes when you have this conflict of signals. So, for example, how do we actually trade off cost versus quality? How do we trade off distance versus ability? And in this particular case, where on the right, you see that we have a provider who we have direct scheduling and preferred partnerships with, but the problem is that we analyze their claims and we thought they have bad clinical outcomes. So what do we do? And one solution is to have a bunch of rules which capture how we want to do all these trade-offs, but we don't have a good we don't have a particularly good grip on what the thresholds should be. How much do we trade off this versus that? And this is where machine learning comes into play. So, like any good data scientist, we have this sort of very classic steps to machine learning. So first, we find some kind of metric function. Then we learn to rank. So that means we find the ranking strategy which optimizes that metric function. And finally, we want to actually make sure that we do what we want to, which is making healthcare affordable and low cost, high quality healthcare affordable for all. Cool. So, let's dive into the first step of our task, which is choosing this metric function. And so before we do that, we want to take a step back and go back to our mission and say, what does it actually mean for a doctor to be good so that we can recommend them? And this is a really really difficult problem. There's a bunch of debate from clinicians, policymakers, whoever, and it's just one of these really difficult problems. And not only that, for our use case, we have to be able to write it in some numbers, and we got to be able to optimize it. And finally, we have to be able to adjust that to accommodate for Oscar's business needs. So one of the things that, we have these posters around the office all of the time, and one of the things that we always say is that we want to refactor healthcare. It means that, so for our case, we actually want to look at quality in a slightly different way, and we want to look at it through data. And what data to give us signals other than what the members actually chose. And I think this is a great signal to derive quality from, because the member actually cares about what kind of healthcare they receive. And we did a first pass through what drives member selections. They largely correspond to the things that we would expect of our doctors, at their cost, distance, how many other people visited them, member experience, availability, and so on and so forth. So now with that idea in mind, where we're trying to derive provider quality through member selections and member visits, now we have to actually start quantifying things. And good, as we said, good ranking algorithms put member selections higher. So we try to quantify using this metric function, and then this metric function is sort of the expected value per query of this thing called discounted cumulative gain. And this, to define our discounted cumulative gain, we use this. This is fairly classic to learn to rank sort of applications. So for example, suppose we're given this list of providers on the right, and the second provider was selected by the member, then we incur a gain of 1 divided by log base 2 of 3. However, of course, we can't actually evaluate this expectation analytically, so we rely on a data set of claims to be able to do that. So now of course, the question is, where do we get this data set? So we first have, the member, they make a request, they make a search request through our app. That comes to some result. And in the corresponding sort of data flow, there is there's a visit. That visit results in a claim. That claim gets put into our claims database. And then we also have a provider roster database. So we have to first map the whatever the doctor put on their claim to the provider in our provider database, and that's done through an NLP process called entity linking, and we were here last year to talk about it. Finally, so once we get that provider, then there's another claims attribution process to link that back to the original search, which resulted in this claim, and these two together go into our sort of learn to rank data set, which comprises of what the query was, what candidates were shown to the member, what rank at which rank, and whether or not they were ultimately selected. And we use that for both model training, which we'll get to later, and as well as for computing our metric function. So one thing you might notice about sort of this system diagram is that not all queries that are issued by the user actually make it into our data set. We only see a query in our data set if it also has a claim, right? And so if we actually go back here, we estimate this per query expectation, but the per claim, once we have this selected data set, that expectation might be biased. So we have to actually quickly debias that. So if we go back to our original slide on study, the actual display rank, we actually have a very big positional bias from our selections. So actually, a lot of members select a doctor that we recommend just because we recommended them. They just trust us that much. So we have to actually come back and debias this. So originally we have what we want to get is this value, which is the expected per query. But however, we have this. What is this now? Oh, sorry. Now we actually have this different data set. So before we have this, we want this Q, but now here it's a little bit hard to see. We want we want this S. What we actually have is this selections data set, which is this S below, and we want to adjust that back to Q. So what we do is we apply a weight to each of the claims, and this is a slight typo here. The weight actually is based on the probability of seeing a claim at a given display position, and it's negative log of that, which corresponds to information content. So here's an example. Actually, we have query. So here we have query 1, query 2. In query 1, some provider at the top position was selected, and in query 2, a provider at position 3 was selected. So our algorithm our metric function then actually places more importance on query 2 because we actually, that's actually a selection at lower position, and that we believe, is a more rare event. It constitutes a stronger form of feedback. So now, if we have a new strategy, which just interchanges these two for each of the queries, we actually rank this new strategy better because we put more emphasis on query 2. And finally, there is some bias that we actually do want. So, numbers may or may not actually have the entire information about the provider. We as insurance may know more. And there are some times where we're confident where, that visit probably shouldn't be something that we're learning from. And so here's one of them. The member visited this provider, and they were not treated very well, and there's even a potential HIPAA violation from the provider staff. So, this is a provider, this is a visit which has clearly gone wrong, and, something, we don't want to include visits to this doctor in our data set. And I should just note that, HIPAA violation is a very severe thing, and we would also pursue contract termination for such in these cases. So this, however, does bias, this kind of bias does sort of tweak, imbalance the training set a little bit. One of the cardinal rules of machine learning is that your training distribution has to match your serving distribution. And then I will show, once we serve the data, I will handle this, we will handle this sort of problem while we're serving the data, serving the model. So how we handle this is mostly by having a 3-stage ranking algorithm. So at the first stage, we have about 20,000 candidates if we're looking for like PCPs in New York. There's about 20,000 candidates that we could consider. And at the first stage, we're mostly applying sort of these kind of filters. We want to apply a lot of business logic filters to, like the ones that we saw here, to this kind of exclusion. So we get back down to about 10,000. And one of the things that, this is sort of, in a more traditional learn to rank framework, we would just do this by filtering them out. But there are some regulatory constraints that we have to include these providers. They have to be theoretically included. And so we do deal with that by just slapping them with an extremely large downrank. So after that's out of the way, we have a sort of very lightweight model. It's a very simple linear model. The weights are chosen based on the various people who work at Oscar. They have a bunch of product knowledge. They have some guess as to how important each factor is to our rankings. And we also previously used a rules model, and some of that knowledge also went in here. And so we take about from this output stage, we have about 10,000 candidates, and at this stage, we're only ranking about we only take 100 candidates, and only at this point do we have the full machine learning model come into play. And this is taking about this is now like the model can do literally whatever it wants using the power of XGBoost, as we may have seen in the previous presentation, and everything. This is all completely data driven. It takes about 100 candidates and serves up about 20 to the user. Getting ahead of myself here. So This is some of the software infrastructure to actually serve the model. It comes as before. It comes in as a request. There's a GRPC wrapper, which goes around Elasticsearch. So one thing I want to sort of this can get really technical, but one thing I do want to point out is that at the gRPC layer, we mostly deal with IDs only. And we have this catch-up logger, which handles logging of all of the internal data lives outside of this gRPC service, which is live. And all of our data set is being compiled in the background, and that feeds into a model training job, which trains some kind of model. It's specifically a black box because I thought that was funny. So back to this, the fact that we're dealing mostly with IDs on the gRPC side. We deal with so much data. That's a recurring theme, I guess. We deal with so much data. Just moving around data is very expensive computationally from the various data sources that we have. So actually, by cutting down on how much data the gRPC service has to deal with, we can actually consider more candidates and improve the quality of the model. So yes, I'm not going to dwell too much on the model itself because this is lots of data science literature on why gradient boost works well and for ranking problems, and but more to do with the fact that we want to be able to serve more candidates, and to do that we need a very good, efficient data pipeline. So once we have this model, we have to make sure that it's doing what we want it to do. That is that we're actually dedicated to the mission of delivering cheap, affordable healthcare, and cheap, high-quality, affordable healthcare. And so one of the things that we have is this kind of sort of satisficing metric. That means that every ranking strategy that we come up with has to satisfy a set of rules. So we expect that the top providers that we recommend, they follow HEDIS guidelines, they're available to book, they're close to our members, and so on and so forth. So there are a bunch of, out of the whole space of ranking functions, there are a bunch of functions which satisfy these conditions. Of course, then there's the optimize. This is in contrast to the optimizing condition, which is the metric function that we spent, 10 slides talking about. And there's only one ranking strategy out of the whole space that optimizes this. So when we're actually testing, we have to make sure that that not only does our new algorithm improve on this optimizing metric, but it also stays within the bounds of these satisfying metrics. And finally, moreover, it's this kind of we're training this model offline. It doesn't have, while offline is a reasonably good proxy for how it behaves in the wild, it's not a substitute. It could be always that things change and we don't know what's going on. So, it's not, this kind of testing is not a substitute for A/B testing. And also, it's not a substitute for product KPIs. So these are things that, your product manager these satisfying metrics are things that your product manager probably wants to keep track of. They probably want to keep track of, all of the top 10 recommended providers. What is their next, what is the average, time until they have an availability? That might be something you keep track of as a KPI measure, and you might set some kind of threshold as a satisfying criteria. However, this doesn't always do that well. So it won't, the satisfying metrics won't help catch the bugs, some bugs like this one. And what's happening is that we added some feature, but we added it wrong, and we kept track. So we tried to add member experience, some kind of member experience factor into rankings, We expect it to go up after we added it in, but we have like all these monitoring systems that monitor these product KPIs. We didn't see it. We didn't actually see them go up, and then we like, oh, okay, there's a bug in here, so we fix that bug, and then we actually see the product KPIs go up. So so this also goes into the issue of how do we actually test ML systems. We follow this Google paper called the ML test score strategy, which means we make sure all of our code generation is very well unit tested. We also have monitorings on not only these KPIs, but also of the feature vector distributions. And also, when we construct the metric function, we've made a bunch of assumptions. We made a bunch of assumptions building our model, and we have periodic model review to make sure that these assumptions always hold. And going back to this slide, we also want to, there's more business strategy concerns that an ML algorithm isn't going to deal with. So first thing is like fairness and data ethics. At Oscar, we made a very conscious decision not to involve the members' health into these rankings because a lot of those things can be quite biased, and we don't, insurance already has like enough of a bad reputation. We don't want to be seen as tracking them, and then also that ML doesn't actually replace business strategy. And one of the business strategy points is that we want to actually maximize the role and engagement that we have, and we want to shape a larger part of healthcare. So this kind of thing is not very well kept track of by some kind of silly metric function. You actually need to go and have like these dashboards, and some C-suite executives to actually look at this and then come up with a business strategy on how you want to deal with rankings. All right, and so going back to this, it's that the ML will not replace your business strategy on how you think about problems in the healthcare space. Finally, I want to come back to how this model review point, where we mentioned earlier, model assumptions change over time, and they require human review. And one thing that's important is that we document all of these review steps. And so, for example, you can actually see, in the past that on June 10th we did one run of the model. We understand that there's a double peak in our selection patterns. One of our selection patterns is because we just don't see as much, or we see different selection patterns within like people of rare specialties. So like I don't know, thoracic surgeons or something, or bariatric surgeons. And then we revisited this very recently, on 22nd of October, and we see that the pattern is still sort of true, but a little bit less pronounced. And this is something that we've got to keep an eye on to be able to going forward. So this is so those are the steps, the 3 steps. Define a metric function, train something, build the pipelines to train something, and then make sure that we're doing what we're doing. Make sure that we get the results we want. I think some things that we learned throughout this process were, one thing is pipelines. We have a huge, we have all of these monitoring pipelines. We have all these monitoring pipelines. We have all these reviews. We have a data pipeline that moves things through the service. We also have a claim attributions pipeline, an entity linking pipeline. All of these. There's like a tremendous amount of infrastructure that needs to be built before we can actually do, before we can even get started on this problem. Never sort of underestimate, how much pipelines can help you. And the second thing that we learned is that testing these things are really hard. It's not entirely clear, even just by inspection, like this recommendation is wrong. Like, so a lot of these things you just don't see. And sometimes bugs just go unnoticed for months, as we saw earlier. We just implemented this feature wrong. It was going into the model wrong, and we didn't see it until like we actually built a product dashboard that says, "Hey, look, your KPI isn't improving. Why is this?" And then I think another thing that has been sort of echoing throughout the talk is that we testing is really important, but the ultimate goal is to make sure that we deliver low cost, high quality healthcare. Like none of the model actually makes sense like if we don't achieve this goal, and a lot of our testing is actually very agnostic to what model we're using. We could very well have used a logistic regression or something. As long as it achieves the results, we would be very happy with that. And finally, machine learning won't necessarily replace a human. There's still a lot of product decisions to be made. You have to look at your product as a whole. You have to have okay. Anyway, you have to have you have to have somebody decide business strategy. You have to have somebody really look at the products as a whole. And optimizing one function isn't the end all be all to everything. This is what we'd like to do more in the future. First is to actually expand our feature set. We've just gotten started with a lot of these data. We would like to really look. Most of our clinical outcome is around preventative care and also around sort of things that we can actually accurately measure through claims. But we would actually want to involve more clinical sort of opinions on our rankings. The second thing that kind of happens is we also always want to improve the quality of provider data. Like, we're only as good as our data, and if we recommend a provider and they're at a phone number which they're not at anymore, you're gonna call that provider and get frustrated. And so we always want to have, always want to make our data more accurate. And another thing about data is that we want to involve more clinical knowledge. This is also sort of echoing the first point, that we want to take clinical knowledge and leverage that for search. One good example is like, what conditions might a throat doctor treat? And we want to have really build out all those knowledge graphs. And finally, we want more of your data. We want this is still like we want more data. Models are only good as the data they're trained on, and give us more data so that we can rank you better. All right, and this is I'll leave it open for questions, and these are our links of you. Yep. Right, so the first question is, how did we label our y variable? Our y variable is labeled based on these claims that we get. So each claim, we actually know which provider it is. It's referring to, and then what the y variable is literally just whether or not the claim was for that provider or not. So our prediction is a score of which we use to rank. So we validate by replaying like all the historical requests. Like, we have a database which we construct of all these historical requests. We can we get this data set. We can sort of hold out a bunch of it, and then run all the standard ML tests. Yep. Yeah, not that different actually, because display rank is like one of display rank is already the biggest, most important factor, which means that we were doing already quite well with rules. But this allows us to handle much more data than what we originally were able to handle, and in more of a flexible way. Yep.
You had mentioned that you use some I don't know if that was like a nurse note or like consumer's like review, but some sort of like text
Yep.
about the visit in order to inform the ranking.
Yep.
How did you go about both linking that like text to the actual provider claim, and how did you use it?
Yeah. So after we have an adjudicated claim, we send out a survey. Like, did you like this provider or not? That actually is both free text and structured, so people can put structured input, like this provider was attentive, this provider had good staff, this provider was easy to contact, so on and so forth. Yep. We ask you to give us more data. We have a preferred partner program, which is basically give us more data, and also we'll work with you to make sure that we have you accurately, and also suggest what possible improvements can be made. All right. All right then. Thank you. Thank you all.
Thank you, Bingjie.